Hi everyone, I am Lap-Loi Chung from the National Center for Research on Earthquake Engineering and from the Departments of Civil Engineering, National Taiwan University and National Chung University. Welcome to the course Introduction to Seismic Design of Structures. This is lecture 10-1, Design Basis Seismic Force 1. Seismic force is used for the design of structures, and design basis seismic force is the seismic force corresponding to the design basis earthquake level. And here are some terminology. Design basis seismic force is the seismic force for the design of a structure at the design basis earthquake level. In Chinese, 设计基准地震. Importance factor in Chinese 用途系数. Importance factor is used to specify how important the building is. First using seismic force amplification factor in Chinese 起始降伏地震力放大系数. Design basis seismic force is an elastic force. After multiplied by the amplification factor, it becomes yielding seismic force. The next one, seismic force reduction factor for structural system due to ductility. In Chinese, 结构系统地震力折减系数. If the structure is ductile, the design seismic force can be reduced by this factor. This is called seismic force reduction factor for structural system due to ductility. Ductility capacity, in Chinese 韧性容量, is the ratio between ultimate displacement and yielding displacement. If the structure has no ductility, therefore the ultimate displacement is the same as the yielding displacement. Therefore, the ratio of the ultimate displacement to the yielding displacement becomes 1. Therefore, the structure has no ductility. The higher the ductility capacity, the more ductile the building. Allowable ductility capacity, in Chinese 容许韧性容量. At the design basis earthquake level, the ductility capacity cannot be fully developed. Only allowable ductility capacity can be developed. Therefore, the allowable ductility capacity is smaller than the ductility capacity. Design basis earthquake is an earthquake with 10% probability of exceedance in 50 years. Or you can call it an earthquake with return period of 475 years. And design basis seismic force is the design seismic force at the design basis earthquake level. From Seismic Design Codes, equation 2-1, we have this formula for the calculation of design basis seismic force. V equal to I divided by 1.4 alpha y times SAD divided by FU modification times W. And V here is design basis seismic force. I here, importance factor. The more important the building, the higher the importance factor. Therefore, the larger the design seismic force. And SAD is the design basis spectral acceleration of the site, SAD. And W is the total structural weight. That's the dead load of the structure. SAD times W can be considered as inertial force of the building. Therefore, the design basis seismic force is proportional to the inertial force of the building. That is the product of SAD and W. Alpha Y is the first yielding seismic force amplification factor. Design basis seismic force is an elastic force. after multiplying by the first yielding seismic force amplification factor, after the multiplication of this amplification factor, the design basis seismic force becomes from linear to yielding seismic force. And Fu is the seismic force reduction factor for structural system. If the structure is ductile, Fu can be large. The more ductile the structure, the larger the seismic force reduction factor. And because it's located in the denominator, the larger the value Fu, the smaller the seismic design force. Therefore, the design basis seismic force is proportional to the importance factor. That's the higher the importance factor, the larger the design basis seismic force. And it is also proportional to the spectral acceleration. The higher the spectral acceleration, the larger the design basis seismic force. And it is also proportional to W, the total weight of the structure. Therefore, the higher the weight, the larger the design basis seismic force. And this is inversely proportional to alpha y. Alpha y is the first yielding seismic force amplification factor. Therefore, the higher the alpha y, the lower the design seismic force. And it is also inversely proportional to Fu, and Fu is the reduction factor. The higher the reduction factor, the lower the design basis seismic force. From Seismic Design Code Section 2.8, we can look up the importance factor of the structure. And the buildings are divided into 4 categories. In Category 1, the building must remain operational for emergency response after earthquake, such as hospital, because this category of building is so important. Therefore, I equal to 1.5. In Category 2, buildings contain considerable amount of poisonous and explosive substances, such as nuclear power plants, because the failure of this building may cause serious damage or serious loss of human lives. Therefore, this category of building is so important. Therefore, I equal to 1.5. For Category 3, the buildings are used by public with high occupant density. Occupant density is the number of occupants per unit floor area, such as department store, because there are lots of people in this category of building. Therefore, I equal to 1.25. Category 4 is other building, other than Category 1, 2, or 3, and it is classified as Category 4, such as residential building, I equal to 1.0. When the importance factors I equal to 1.25, the design seismic force is 25% more than that with the importance factor I equal to 1.0. For the building with importance factor 1.5, the design seismic force is 50% higher than that for the building with importance factor 1.0. Therefore, the design seismic force is proportional to the importance factor. The higher the importance factor, the larger the design seismic force. And here's an example. A residential building located at Ruishui Township, Hualien County, and within 2 kilometers from Yuli Fault. The site is hard site. And in this problem, in this question, we are going to find the importance factor of the building. Because the building is a residential building belonging to Category 4. There's others building. Therefore, its importance factor from the previous line, the importance factor for Category 4, I equal to 1.0. Therefore, the importance factor here, I equal to 1.0. Next, we move to the spectral acceleration. Design basis spectral acceleration for site class 1, 2, or 3, SAD, and the unit of SAD is G, gravitational acceleration. And SAD, the special acceleration, can be described by this formula. And the response spectrum is divided into 4 segments. In the first segment, when t is less than or equal to 0.2 T0D, SDS equal to SAD equal to SDS times 0.4 plus 3t divided by T0D. Therefore, the special acceleration is linearly increasing with the structural period t. When the structural period lies between 0.2 T0D to T0D, SAD is constant, SAD equal to SDS. And when the structural period lies between T0D and 2.5 T0D, and SAD is inversely proportional to the structural period t, SAD equal to SD1 divided by t. When t is larger than or equal to 2.5 T0D, SAD is constant, that's the lower bound of the special acceleration. SAD equal to 0.4 times SDS. And T0D can be computed by SD1 divided by SDS. Therefore, the special acceleration can be fully described by 2 parameters. One is SDS, the other is D1. And the T here is the fundamental vibration period of the structure, and the unit for T is S second. And the damping ratio of the structure is fixed to be 5%, that is 0.05. We have just talked about the special acceleration for sites 1, 2, or 3. Then we move to the design basis special acceleration for Taipei Basin, SAD, and the unit of SAD is G, gravitational acceleration. Similar to the previous slide, the special acceleration also divided into 4 segments. But instead of the parameter SD1, it is replaced by T0D. Therefore, SD1 here is replaced by SDS times T0D. In the first segment, when T is less than, the structural vibration period is less than or equal to 0.2 T0D, and the special acceleration is linearly increasing with the structural period T. When T lies between 0.2 T0D and T0D, SAD is a constant equal to SDS. In the third segment, when T lies between T0D and 2.5 T0D, SAD is inversely proportional to the structural vibration period T. Therefore, SAD equal to SDS times T0D divided by T. When T is larger than or equal to 2.5 T0D, and is the lower bound for the special acceleration, SAD equal to 0.4 times SDS. And the T here is the fundamental vibration period, and the unit is second, S. And the damping ratio of the structure equal to 5%, that's 0.05. And here's the example again. A residential building located at Ruishui Township, Hualien County, and within 2 kilometers from Yuli Falls. And the site is hard site, class 1, and the building is reinforced concrete with moment-resisting frame. It's a 2-story building with story height of 3 meters, and the total height is 6 meters. And in this problem, we are going to find the design special acceleration SAD for the structure. From Seismic Design Code Section 2.6 Equation 2.10, we can have the approximate fundamental period of the reinforced concrete structure with moment-resisting frame and without non-structural rigid wall, shear wall, or other lateral force-resisting member. And the structural vibration period can be approximated by this formula, T equal to 0.07 Hn to the power 3/4, and Hn here is the height of the building. That's the elevation of the roof from the ground of the structure. In this case, is 6 meters. Therefore, T equal to 0.07 times 6 to the power 3 divided by 4 equal to 0.268 seconds. Right now we have the importance factor I equal to 1.0 and the fundamental vibration period of the structure T equal to 0.268 seconds. And from the previous lecture, we have already found SDS equal to 1.136, SD1 equal to 0.711, and from SD1 and SDS, we can have T0D equal to SD1 divided by SDS equal to 0.626 seconds. And the structural vibration period here lies between 0.2 T0D to T0D. There's a 0.1252 seconds to 0.626 seconds. Therefore, SAD is constant, is equal to 1.136. So far, we have the importance factor of the building I equal to 1.0 here. SAD equal to 1.136. And in this question, we are going to find the total weight of the structure. That's the dead load of the structure, W. From the dimension of the building, from the dimension of the element, and from the weight of those non-structural elements, we can calculate the dead load of the structure. After calculation, the second floor weight is found to be W2F equal to 79.10 ton force. And the weight of the roof floor, WRF, equal to 66.95 ton force. And the total weight of the structure, equal to the summation of W2F and WRF, equal to 146.05 ton force. Therefore, so far, we have the importance factor I equal to 1.0, the spectral acceleration, SAD equal to 1.136, and also the W, the weight of the structure, equal to 146.05 ton force. And we are going to find the first yielding seismic force amplification factor alpha Y. Under design basis seismic force, the structure remains elastic. And if the design seismic force is amplified by alpha Y times, then the seismic force becomes the yielding seismic force. Therefore, after the design seismic force is amplified by alpha Y times, and first yielding in some member occurs. And the amplification factor alpha Y depends on two factors. One is the design method, the other is the loading combination. And from Seismic Design Code section 2.6, if the building is reinforced concrete structure designed by ultimate strength design method, and the load factor of seismic force is 1, then the first yielding seismic force amplification factor alpha 1 equal to 1.0. This is the force displacement relationship of a structure under earthquake. Delta here is the displacement of the structure, and P here is the force of the structure. When the displacement is small, it is linearly related. The seismic force the force of the structure is linearly related with the displacement. When the displacement becomes larger and larger, the structure becomes softened, and the stiffness of the structure becomes less, and it enters into nonlinear range. Therefore, PD here is the design seismic force, and PY here is the yielding seismic force, and PU here is the ultimate seismic force. And this graph is taken from the Seismic Design Code figure C2-1. And PD here is the design seismic force, And after multiplied by alpha y, PD multiplied by alpha y, it becomes Py, and Py is the yielding seismic force. Py here is the yielding seismic force. And if it is further multiplied by 1.4, and it becomes Pu, and Pu is the ultimate seismic force. And 1.4 here counts for the redundance of the structure and the strength hardening of the structure. And 1.4 here, the reason to have 1.4 times is that because the structure itself is redundant, and the redundance of a building is so high, and the material itself have a strength hardening property. Therefore, we have 1.4 here. And we go back to the example. So far, we have the importance factor I equal to 1.0, the spectral acceleration equal to 1.136, and the weight of the structure equal to 146.05 ton-force. And in this question, we are going to find the first yielding seismic force amplification factor alpha y. The same residential building located at Ruishui Township, Hualien County, and the site is hard site, class 1, and the building is reinforced concrete structure. And we are going to find the first yielding seismic force amplification factor alpha y. The building itself is a reinforced concrete structure and designed by ultimate strength design method. And the load factor in the loading combination of the seismic force is 1. Therefore, from Seismic Design Code, section 2.9, we have the first yielding seismic force amplification factor alpha y equal to 1.0. And here's the reference for this lecture. The first reference is Seismic Design Code of Building, and it is published in 2011 by the Ministry of Interior. And here's the video for Lecture 1, Lecture 2, Lecture 3, Lecture 4, Lecture 5, Lecture 6, and Lecture 7, Lecture 8, Lecture 9, and Lecture 10 here. Lecture 10-1, and this video is under construction, but the Chinese version has already been posted to YouTube. And in this lecture, we talk about design seismic force, and the design seismic force is determined by importance factor I here, design basis spectral acceleration SAD here, W, the total weight of the structure, that's the dead load of the structure, and alpha y, first yielding seismic force amplification factor here. And in this lecture, we have already talked about I, importance factor, SAD, design spectral acceleration, W, total structural weight of the structure, and alpha y, first yielding seismic force amplification factor of the structure. And in the next lecture, we will talk about seismic force reduction factor for structural system due to ductility. That's all for this lecture. Thank you. See you next time. Bye-bye.